you try your best but you don't succeed, when you get what you want but not what you need, when you feel so tired but you can't sleep, stuck in rivers, and the tears come streaming down your face, when you lose something you can't replace, when you love someone but it goes to waste. Could it be worse? Lights will guide you home and ignite your bones, and I will try to fix you.
Where am I? I just want to leave, but the stupid door won't open.
Ah, yes, my child. There is a way to open this door, but it's not so simple as a lock and key. We must use our knowledge of calculus to derive an equation, but you don't need a college degree. Let's flash to a place where I can show you a method made by me. Suppose we wish to approximate the solution to the initial value problem dy over dx is equal to f of x comma y, where y of x naught is equal to y naught, at x is equal to x1 at x naught plus h, where h is small. The idea behind Euler's method is to use the tangent line to the solution curve through x initial, y initial to obtain such an approximation. The equation of the tangent line through x initial, y initial is y of x is equal to y initial plus m of x minus x initial, where m is the slope of the curve at x initial, y initial. According to the equation, m is equal to f of x initial, y initial, so y of x is equal to y initial plus f of x initial, y initial multiplied by x minus x initial times 0.5. Setting x equal to x1 in this equation yields the Euler approximation to the exact solution at x1, namely y1 is equal to y initial plus f of x initial, y initial multiplied by x1 minus x initial, which we write as y1 is equal to y initial plus hf times x initial, y initial. Setting x equal to x1 in this equation yields the Euler approximation to the exact solution at x1, namely y1 is equal to y initial plus f of x initial, y initial multiplied by x1 minus x initial, which we write as y1 is equal to y initial plus hf multiplied by x initial, y initial. Now suppose we wish to obtain an approximation to the exact solution to the initial value problem 1.10.1 at x2 is equal to x1 plus h. We can use the same idea, except we now use the tangent line to the solution curve through x1, y1. The slope of this tangent line is f of x1, y1, so that the equation of the required tangent line is y of x is equal to y1 plus f of x1, y1 multiplied by x minus x1. Setting x equal to x2 yields the approximation y of 2 is equal to y1 plus hf multiplied by x1, y1, where we have substituted for x2 minus x1 is equal to h to the solution to the initial value problem at x is equal to x2. Continuing in this Continuing in this manner, we determine the sequence of approximations y of n plus 1 is equal to y of n plus hf multiplied by xn comma yn. N is equal to 0, 1, and so on to the solution to the initial value problem at the points x of n plus 1 is equal to x of n plus h. In summary, Euler's method for approximating the solution to the initial value problem, y is equal to f of x comma y of x initial is equal to y initial at the points x of n plus 1 is equal to x initial plus n times h, multiplied by n is equal to 0, 1, and so on, is y of n plus 1 is equal to y of n plus hf, multiplied by x of n, y of n is equal to 0, 1, and so on. Here, Sonny, why don't you read me the problem?
Okay. Use Euler's method starting at x equals 1 with two steps of equal size to approximate f of 0. Show the work that leads to your answer.
You see, we begin with the differential equation 1 minus y. Since we also have the initial condition f of 1 equals 0, we're going to start a little table to find our results. So I'm going to start with my x of n column. We're starting with our initial condition of 1. And if we're trying to get to 0, what would be a step of an equal size?
0.5. Negative 0.5.
Correct. In the next column, the y of n column is the column that's going to direct us towards our solution. We know that our initial condition, f of 1 is equal to 0, means that the first y will be equal to 0. Now we'll use our next column and use the equation within the next column to find the new y, which will add on to the initial condition. So for this column, we'll use our differential equation and multiply it by the change in x. So we would have 1 minus y times dx. What do you think dx may be?
Well, from here it goes from 1 to 0.5, so negative 0.5?
Correct. So we would have 1 minus 0, our original y, times negative 0.5. Can you tell me what our new y would be?
Negative 0.5.
Correct. Now our equation changes because our next y of n value is equal to negative 0.5. Now, what would be our next y value? Plug into the equation.
Well, let's see. So 1 minus y, so 1 minus negative 0.5, so 1 plus 0.5 times negative 0.5, so it's 1.5 times negative 0.5, negative 0.75.
Correct. Our next new y is negative 0.75. Now the last step that we have to do is to add on the new y to our second y, and that would be equal to
negative 1.25.
Correct. See, with all these steps, it's pretty simple. You just have to follow our equation, and you'll get to the answer. And we got to our solution in 2 steps.
Thanks, Euler. Gee, thanks, Euler.
No problem, bucko.
Oh. Problem solved? Oh no! How am I supposed to cross the street if I don't know the car's position?
Hi, I'm Leibniz, the creator of the reverse chain rule and the chain rule.
Hey, maybe you can help me cross the street.
Yeah, if you have the function for the velocity of the cars, we can integrate it to find the position.
Oh, wow.
Let's go!
According to the chain rule, the derivative of a composite function w of u of x is the derivative of w multiplied by u of x, then again multiplied by the derivative of u of x. With u substitution, we are taking this form and finding the antiderivative w of u of x. Integration by substitution can be derived from the fundamental theorem of calculus. When the integrand is in the form y is equal to the integral of f of v of x multiplied by the derivative of vx dx, such as the integral of cosine x squared multiplied by x dx, you can integrate it with substitution. The chain rule for integration holds that dy over dx is equal to dy over du multiplied by du dx. Thus, dy is equal to dy over du multiplied by du dx multiplied again by dx. Y is equal to the integral of the previously stated function, in which the dx's cancel out and we are left with the integral of dy over du multiplied by du. Let's consider the problem y is equal to the integral of cosine x squared times x dx, in which u would be equal to x squared. Note that u has to be the function of another function. In this equation, u is the function of cosine. dy over du equals cosine u, and du over dx is equal to 2x. X dx is equal to 1/2 du. Now we have our equation in which y is equal to the integral of dy over du times du, and we can substitute in our variables to end up with the integral of cosine u times 1/2 du. Now we move the 1/2 to the outside, so we end up with 1/2 times the integral of cosine u du, in which we integrate cosine and end up with 1/2 sine u. Now we can substitute u for x squared to end up with 1/2 sine x squared plus c, in which the u substitution rule is proved in the case that it equals the integral of dy over du times du. Now, let's solve our problem.
Okay, Sunny, so here we have the function for the speed of the cars, 2x cosine x squared dx. If we integrate this function, we'll have the function for the position of the car so you can cross the street safely.
And then plug in time for x and we'll know the position of the car at that time.
Yes, so using u substitution, in which we take the derivative of one variable and plug it into the equation, we'll have u is equal to x squared, which is what we'll substitute back in, and we'll have du is equal to 2x dx because we moved the dx to the other side.
And when we integrate, the du will disappear.
Correct. So we're going to integrate the function, because we have taken out the 2x and the x and substituted the x squared for u, so we have cosine u du. Now what's the next step?
Well, the integral of cosine would be sine, so sine u.
Yes,
and
the
du
du
disappears.
goes away because we integrated. Now we just have to plug u back into the function.
And u is equal to x squared.
Correct. So it'll be sine of x squared.
Don't forget plus c. Plus c.
Correct. You always got to remember the plus c when taking the integral.
Thank you so much, Leibniz. Now I can remember how to cross the street more safely. How did I get here? Who are you? I'm just trying to escape this town where I keep being confronted by calculus. I need to walk this path. I think it might be a way out.
Oh, I would love to let you pass, but you still have so much to learn before starting your AP test. Let's begin with my rule, which is one of the best ways to approximate integrals. Not too long ago, I was an aspiring mathematician just like you. Here's how I derived it.
So my rule is based on the fact that if you're given 3 points from a function, you can find a quadratic equation through those points. So for example, say you had the points 3, 12, 1, 5, and 5, 9. With these points, you can create a system of equations. Simplified, these 3 equations would be equal to 12 is equal to 9a plus 3b plus c, 5 is equal to a plus b plus c, and 9 is equal to 25a plus 5b plus c. You can solve this system of equations however you wish. Both elimination and substitution work well. After solving the system of equations, you get a is equal to negative 1.25, b is equal to 8.5, and c is equal to negative 2.25. So the quadratic equation would be y is equal to negative 1.25x squared plus 8.5x minus 2.25. This helped me approximate integrals because when given an integration problem, you can use the endpoints and midpoints as your 3 points the quadratic equation will go through. Then integrate the quadratic equation. A simple way to integrate quadratic equations in the interval a, b is to do parentheses b minus a divided by 6 multiplied by f of a plus 4f of m plus f of b. So you don't even need to solve for the quadratic in the first place.
Okay. That all makes some sort of sense, but how do I know I'm going to be able to use this on the AP test?
Okay, so you're given the function x cubed and you have to integrate it from 2 to 10. Using Simpson's rule, we would take the equation where the change in x divided by 3 is multiplied by the first initial without a coefficient, then by 4, then by 2, and this alternates until you've made it to the last x of n in which there is no coefficient. So to find the change in x, we take b minus a, the integral, divided by the number of steps you're using, which is n, and we find, if we were to use it with this function from 10 to 2, and we're using 4 steps, it would be 10 minus 2 over 4, which is equal to 2. So now on the outside, we're multiplying our function by 2/3. Now, we take the first f of 2 as our first step, then we multiply it by 4 times f of 4, so we're stepping in 2, then 2 times f of 6, plus 4 times f of 8, and on our last step there's no coefficient, so it's f of 10. Now we find each of these numbers by putting them into our equation, in which we would have to distribute this out. And with each number, then when they are added up, it's equal to 2,496. And if we were to take the integral normally, we would find the same exact number.
Wow. Thank you so much, Simpson. I never thought I would like approximating integrals. I still don't like it that much, but this will make a problem on my AP test a lot easier.
No problem, young boy. These methods may seem confusing at first, but it only takes brief understanding of where it came from and where to apply it, and they can be very useful for you. You still have so much to learn about calculus. Good luck on the rest of your journey.
My brain's so tired of all this calculus, but I have to keep going. I gotta get out of here. Bye, Simpson. Who are you? Just please tell me what I have to learn this time. I'm getting really tired of these surprise visits.
Be patient. If you ever want to grasp calculus fully, you have to understand the differential calculus primary theorems. If you've ever heard of the mean value theorem, what I'm about to teach you is very closely related to it.
Okay, but how is this theorem even applicable to real life?
Well, let's say a truck driver drives 163 miles on a toll road with a speed limit of 70 miles per hour. The trucker completes his journey in 2 hours. You need to figure out why he received a speeding ticket at the toll booth. My theorem applies to this problem because of the function of the speed of the car, which is continuous on the closed interval and differentiable on the open interval, basically meaning that there are no discontinuities. We know that the average velocity has to be equal to the instantaneous velocity, and since average velocity is equal to displacement over time, then the trucker would have been going 81.5 miles per hour at one point, which is well over the speed limit.
So what you're saying is I can never drive over the speed limit?
No. Let's recap.
Thanks, Roll. Now I feel a lot more ready for my AP test. Oh, I can finally get out of here. That was the most helpful dream I've ever had. I'm pretty ready for my test now. What day is it? Saturday. Oh no! The AP fees were due yesterday!